Hi everyone, and welcome to this video on recurrence relations. Now, let's have a look at this sequence. So, we've looked at sequences for many years in mathematics, and normally when you see that, you would write something like un, nth term. This is going up in 2, so it must be related to the 2 times table, but you should be able to see this is 1 more than the 2 times table. That's fantastic. That is a formula that will allow us to find missing terms in this sequence. Now that's great when things follow a linear pattern or even quadratic pattern, but some sequences, you'll see them later, it's very difficult to write an nth term. So we had to form a different way. So what we started to look at, if we call this one U1, U2, like the first term, second term, just the same as we would have done with the nth term, what we start to see is, well, the rule is +2. So we could say, well, the second term, well, that's equal to the first term, add 2. And the third term is equal to the second term, add 2, and so on. Yeah? So the fourth term is the third term, add 2, and we can continue that on. Now, what we started to do is see a link between, obviously, there's always one less. So we had a choice here, but what we went for is, on the right hand side of the equals, if we called that un +2, what would we write here? Well, it's always one more, isn't it? So we said this, and this is what we mean by recurrence relation, so this sort of notation. And this is great. This is a way of writing this. And yes, we have a normal nth term, but just entertain me for the minute. If it was more difficult, but you could still see a pattern, you could use this. Now this is great, but this would also be the formula for, say, this one. So we can't have a formula which gives us, well, in fact, an infinite amount of possibilities. So we had to make another adjustment really to this. So what we always have to do is put a little comma, and we have to say what the first term is. So that's for that one, but for this one it would be the same, but U1 would equal 7. Another handy way of thinking about this is a lot of people say the next term is the previous term add 2. I'm a fan of that. I don't tend to do it too much. I'm more of a fan of subbing in and writing the formulas, and you'll see what I mean as we go. So you can see here's the notation. I'm only going to do one of these. They're exactly the same really, it'd be a waste of time. But find the first 4 terms. The bit I'm interested in is your structure, not rushing, because when it gets harder you're gonna fall down. So I want to see you say, right, when n is 1, well, what happens when n is 1? n plus 1 is 2. When n is 1, I get that plus 4. But I know the first term is 7, so I can see the first term add 4, so 7 add 4 is 11. Then I want you to write when n is 2. And when n is 2, we're going to get the third term. That is equal to the second term, 2 for n, plus 4. So that's 11 plus 4, and that's 15. And I know you can just quickly rattle these off, but you've got to get in good habits. So when n is 3, we get the fourth term, 3 plus 1, equals the third term, is subbing in this n for this 3, plus 4, and we get 19. So just to finish off, I would write 7, 11, 15, add 19. And in English words, this means the next term is the previous term add 4, but please get in good habits now. How about this one? Maybe a bit harder to see. Pause the video, have a go. I've spelt this wrong, that should be an E there, I do apologise. Okay, hopefully you've had a go, and this one is another example of what I was talking about earlier, hard to write an nth term, because you can see here the difference is 7, but now it's not. So the recurrence is much easier. So hopefully you've seen that to get from one term to the next, I have to multiply it by 2 and then add 1. So to get to the next term, I have to take the previous term, times it by 2, and add 1. And I have to specify that first term must be 6, and if I don't do that, there's an infinite amount of sequences this could be, and I want it for this one. This one's a good one, very similar to Fibonacci. I just missed a 0 and a 1 off. So how would you write this? Have a think, pause the video, have a go. So this is a little bit more tricky because you can see to make the third term, so I'm going to write this, U3, the third term is the first term plus the second term, and the fourth term is the second term plus the third term. Hopefully you've seen that. So if we call this one n, or even this one n, it doesn't really matter. So if we call that n, well, the one on the right is 1 more, and the one on the left of the equal sign is 2 more of this value, and there you go. Now that again has an infinite amount of sequences, so you could start the Fibonacci sequence at any point and it would work for all of them. So we have to specify U1 to be 1 for this example, but we also have to say what the second one is as well. So if your recurrence uses 2 different values, you have to specify 2 just to make sure it matches. I've never ever had a student get this right before. So pause the video, have a go. Hopefully you've not spent too much time on it. This was last week's lottery numbers. You can't write a recurrence formula for this. If you could, you'd be a very rich man, just for the bants. So yeah, don't be too angry with me. Right, look at this. This looks great, doesn't it? So now we have a sequence A1, A2, A3 is defined by, right, so we've got the first value. So I think it's always good to just write the sequence, so P. We've got this recurrence formula, that's great. We're told n is greater than or equal to 1, but we're also told p is less than 0. And we have to show this. I love show that because when you get it, you get that warm fuzzy feeling. If you don't get it, then you just keep going until you do. Right, so this is talking about the third term. And that's great because I've got a recurrence formula. So if I know the second term, I'm all over it. But I don't. So to find the third term, I've got to find the second term first. So for part A, to find the second term, n would be 1. So when n is 1, put in 1 into here, we get the second term. And when n is 1, we get the first term being squared, take away 1. Now the first term is p. So the second term is p squared, take away 1. Now when n is 2, we're going to get the third term, putting 2 in here. When n is 2, we've got the second term, all being squared, take away 1. The second term was p squared, take away 1. And that's being squared, and then we take away 1. So we're going to multiply this bracket out. So first terms, p squared times p squared. The outer terms, we're going to have minus p squared, and that's the same for the inner terms as well. So we're going to have minus 2p squareds, and the last terms will be plus 1. And you can see the minus 1, but they're going to cancel each other out, and I end up with this. And that is here. So I'm just going to make some space, I'm just going to see if yeah, good. So I wanted to leave that top bit there for the sequence. Right, part B. Oops. Part B. So given that the second term is 0, okay, great. So here we have an expression for the second term, so therefore 0 must be equal to p squared minus 1. This is dots, so let's do it the other way, just so you're aware that you don't always have to use dots. So if we add 1 to both sides, square root both sides, we're going to get plus or minus 1. And this is when you have to just remember this bit of information over here. P must be less than 0, so therefore P equals minus 1. I'm just going to double underline that for later. So we've done B. Right, C, bit of sigma notation. So we're putting everything together today. I'm just going to change colour so we can easily see the work. Right, so we've got to find the sum of this sequence, so A subscript R, starting at 1, going all the way up to 200 terms. Wow. So what this means is A1 plus A2 plus A3 plus A4 plus all the way to 200. So it's not too bad. Just have to find out whether it's a geometric or arithmetic sequence and then use the formulas. But you'll see in a minute there's a little trick to this question, and you can always identify it's going to be a trick when this number is massive, normally anyway. So A1, well, we know that is P, and we know P is minus 1. Put that in brackets, it's a negative number. A2, we know that is P squared minus 1. So minus 1 squared is 1, take away 1 is 0. So the third term, we've also got that. So that is P to the power of 4, so even power, so this is going to be a 1 when we square it. Another even power, so it's 1, take away 2 lots of 1, 1 take away 2, we have another minus 1. What do you think A4 is going to be? Well, I could leave you to work it out for yourself, but take my word for it. So if you put n to be 3, get the fourth term, you're going to get an expression that when you sub in minus 1 into it, you get 0. And this is actually called a periodic sequence that repeats, and we would say this has an order too. You're going to hear me talk about that in a future video. I probably could have mentioned that earlier, but this is going to keep repeating. Now, if you notice, the odd values, in the sequence are minus 1, and all the evens are 0, so we know that's going to be a 0. So, how many minus 1s would we have? Because we've got to add them all up. Well, if there's 200 terms, half of them are minus 1, the sum would be minus 100, because we'd have 100 of those. And D, we can do that without going much further. The value of the 199th term, well, it's odd, yeah? So all the odd ones are minus 1. So A, 199 equals minus 1. Let's see if I've got another one. No, I haven't. Okay, so I'll call this video short now. I was going to keep going with the next bit, but we'll make this in 2 different videos, and then I'll give you some instructions of what I'd like you to do with them.